For nearly 3 years, the James Webb Space Telescope had been doing something scientists already considered miraculous, studying planets beyond our solar system that other instruments had already found. It measured their atmospheres. It read their chemistry. It confirmed suspicions raised years earlier by fainter, less capable telescopes. But it had never once found something entirely new by simply looking and seeing it directly, the way you or I might look up and spot a faint light in the sky. Every single exoplanet Webb had touched, in nearly 3 years of operation, had already been discovered by somebody else using some other method, long before Webb ever turned its mirrors toward it. Then, in the summer of 2025, that changed. Astronomers pointed Webb at a young, faraway star blocked out. Its blinding light, using a piece of hardware built specifically for this purpose, and captured something that had never existed in any catalog, any database, any previous observation. A single, faint, glowing point of infrared light sitting exactly where theory said a planet should be hiding and where nobody had ever actually seen one before. This is the story of TWA-7b, the first planet the James Webb Space Telescope ever found entirely on its own, and why the way scientists found it may end up mattering just as much as the discovery itself. To understand why this moment was such a genuine milestone, you first need to understand just how absurdly difficult it is to directly photograph a planet orbiting another star. Since the first exoplanet orbiting a sun-like star was confirmed back in 1995, astronomers have gone on to identify nearly 6,000 worlds beyond our own solar system. But the overwhelming majority of them were never actually seen. They were inferred, detected indirectly, most commonly by watching a star's light dim slightly and predictably as an unseen planet passes in front of it, a method called the transit technique, or by measuring the subtle gravitational wobble a planet's pull induces in its host star. Both methods are remarkably powerful, and both have given us the vast bulk of everything we know about worlds beyond our own. But neither one involves anyone actually looking at the planet itself. Direct imaging, capturing an actual photograph of a planet's own light, separate and distinct from its star, is a completely different and vastly harder challenge, and it is exactly the kind of challenge Webb was, in theory, built to eventually take on. The core problem is almost absurdly simple to state and brutally difficult to solve. As lead researcher Anne-Marie Lagrange, an astrophysicist at France's National Center for Scientific Research, put it plainly, the basic problem is that the star is bright and the planet is very faint. That understates it considerably. A typical star can outshine an orbiting planet by a factor of 1 billion or more in visible light, and even in infrared wavelengths, where the contrast improves somewhat, the imbalance remains staggering. Trying to photograph a planet next to its star is a bit like trying to photograph a firefly hovering directly next to a lighthouse beam, on from miles away, while the lighthouse is actively blinding your camera. For most of the history of exoplanet science, this made direct imaging viable only for the largest, hottest, youngest planets, orbiting at unusually wide distances from their stars, planets still glowing with the residual heat of their own formation, bright enough to occasionally punch through the glare. Even then, the list of exoplanets ever successfully photographed directly numbered only in the dozens, a tiny fraction of the thousands known to exist. Webb was given a specific tool to push past this limitation, an instrument called a coronagraph, built directly into its mid-infrared instrument, or MIRI. A coronagraph works essentially like a precisely engineered mask, physically blocking out the concentrated light of a central star so that fainter light sitting nearby, light that would otherwise be completely drowned out, has a chance to actually register on the detector. Even with that blocking mask in place, some scattered starlight inevitably leaks through, smeared and distorted around the edges of the image. Scientists then have to apply sophisticated image processing techniques afterward, essentially digitally subtracting the remaining glare to reveal whatever faint signal might be hiding underneath it. It is a delicate, technically demanding process, part hardware, part software, and it is precisely the technique Lagrange and her international team used when they turned Webb toward a young star called TWA-7, sitting roughly 111 light-years away in the southern constellation Antlia. TWA-7 was not a random target. Astronomers had been quietly fascinated by this particular star for years, for a very specific reason. Unlike most stars with debris disks, the vast rings of leftover dust and rocky material that surround young stellar systems and often mark the early stages of planet formation, TWA-7's disk happens to be oriented almost perfectly face-on as seen from Earth, rather than tilted edge-on the way most debris disks appear. That geometric accident turned out to be enormously useful. Instead of seeing the disk as a thin, hard-to-interpret sliver of light, astronomers got a clean, direct, top-down view of its full structure, and what they saw inside that structure was 3 distinct concentric rings of material, separated by conspicuous, well-defined gaps. In the world of planet formation, Gaps like that are rarely accidental. They are usually the signature of something massive orbiting inside them, gravitationally clearing out material as it goes, carving lanes through the debris the way a plow clears a path through snow. For years, researchers studying TWA7's disk suspected a planet had to be hiding in one of those gaps. Nobody had ever actually seen it. When Lagrange's team finally processed Webb's coronagraph data, that suspicion turned into something concrete. Sitting precisely within one of those predicted gaps, at a distance from its star roughly 50 times greater than the distance between Earth and our own sun, was a single, faint, unmistakable point source of infrared light. The team calculated its likely temperature at somewhere close to 120 degrees Fahrenheit, still relatively warm for something so far from its star, consistent with a young planet still radiating away heat left over from its own formation. Its estimated mass came out remarkably close to Saturn's, and its position was not just plausible. It was, in Lagrange's own words, exactly where we expected to find a planet of this mass, matching almost precisely what theoretical models of the disk's structure had predicted years before Webb ever confirmed anything was actually there. Scientists take claims like this seriously, but they do not take them lightly, and to their credit, Lagrange's team built in real, honest skepticism before ever going public. There remained a small but genuine possibility, calculated at roughly 1/3 of 1%, that the faint infrared source they had captured was not a planet at all, but a distant background galaxy happening to sit in almost the exact same line of sight, a kind of extraordinarily unlucky cosmic coincidence. Simulated images directly against what Webb had actually captured. The simulations matched. As Lagrange later explained, that alignment between prediction and observation was really why the team became confident there truly was a planet sitting there, not a random contaminating object, drifting through the background by chance. The result, published in the journal Nature in June of 2025, formally introduced the world to TWA7b, a newly discovered exoplanet found by direct image entirely on Webb's own initiative for the very first time. The significance of this discovery goes well beyond simply adding one more entry to an already crowded catalog of nearly 6,000 known exoplanets. TWA7b holds a specific, measurable distinction. It is roughly 10 times lighter than any exoplanet ever, successfully directly imaged before it. Every previous direct imaging success, going back to the very first confirmed direct exoplanet images captured in 2008, had been limited to unusually massive, unusually bright planets, typically several times the mass of Jupiter, simply because anything smaller and fainter had, until now, been effectively invisible against the glare of its star. WA7b, at roughly the mass of Saturn, sits in a completely different, previously inaccessible category, proving for the first time that instruments like Webb's coronagraph can now reach meaningfully further down the mass scale than anything that came before it. Matilda Malin, an astrophysicist at the Space Telescope Science Institute and a co-author on the discovery paper, framed the achievement in exactly those terms, explaining that Webb has effectively opened an entirely new window in terms of both the mass of a planet and its distance from its star, into a category of exoplanets that had simply never been accessible to direct observation before. Lagrange echoed that same point, even more directly, telling Reuters that this newly opened window matters enormously for exploring the genuine diversity of exoplanetary systems across the galaxy, and for understanding how planets, including quite possibly ones like the smaller, rockier planets scattered throughout our own solar system, actually form and evolve over time. There is a second layer to this discovery that deserves real attention too, because it represents something that had genuinely never happened before in the entire history of exoplanet science. If TWA7b truly is the object sculpting those clean, well-defined gaps in its star's surrounding debris disk, and every piece of evidence gathered so far strongly suggests exactly that, then this marks the very first time astronomers have directly imaged a planet that can be conclusively tied to actively shaping the structure of the disk it formed within. For years, scientists studying debris disks around other stars had inferred, indirectly, that unseen planets were likely responsible for the gaps, rings, and warps they observed, essentially reading planetary fingerprints left behind in swirling dust without ever actually seeing the hand that left them. TWA7b represents the first time that inference and direct observation have lined up completely, a hidden architect finally caught, quite literally, in the act, still shaping the raw material of its own young solar system in real time. It is worth pausing to note, with the same honesty that should accompany any genuinely new scientific claim, that TWA7b's status is still formally described by its own discovery team as a strong planetary candidate rather than an absolutely, permanently confirmed planet, precisely because that small statistical possibility of a background object can likely never be reduced all the way to zero from a single set of observations alone. Further monitoring, tracking the object's position over time to confirm it moves together with its star rather than sitting motionless as a distant background galaxy would, will ultimately provide the final, decisive confirmation. But the weight of evidence assembled so far, the precise positional match with theoretical predictions, the successful computer modeling, the physically consistent temperature and mass, has already convinced the overwhelming majority of the scientific community that this is exactly what it appears to be. A genuine planet, seen directly for the very first time by an instrument built specifically to make moments like this possible. It is also worth remembering that this was not, technically, Webb's very first encounter with an exoplanet in image form. Back in January of 2023, Webb had confirmed the existence of a previously suspected exoplanet using its imaging capabilities, a planet that other, less powerful instruments had already flagged as a likely candidate years earlier. That earlier moment was a genuine achievement in its own right, proof that Webb's instruments could reliably verify what other telescopes had only guessed at. But TWA-7b is something categorically different. Not a confirmation of an old suspicion, but a discovery starting from nothing, a planet nobody had ever detected by any method, found purely because Webb was sensitive enough and its coronagraph precise enough to see something genuinely new sitting in the dark for the first time in human history. Astronomers are already looking ahead to what this capability could eventually mean. If an instrument built primarily to study the early universe, galaxies, and star formation can now also directly image a planet with roughly the mass of Saturn, sitting more than 100 light years away, hidden within the glare of its own star, the natural next question becomes just how much further down that mass scale future observations, refined techniques, and even more capable successor telescopes might eventually be able to reach. Nobody is currently claiming Webb, or any telescope currently operating, is anywhere close to directly photographing a small, rocky, Earth-sized planet around another star. That remains a genuinely enormous technical leap beyond what was achieved here. But TWA-7b proved something that, until the summer of 2025, existed only as a hopeful theoretical possibility, that the gap between what we can indirectly infer about distant planetary systems and what we can actually directly see with our own instruments is finally measurably beginning to close. A star, a disk of ancient dust, 3 quiet rings with a gap carved cleanly between them and sitting exactly where the mathematics said it had to be, a single faint point of infrared light nobody had ever captured before. That is what it took to add one small, genuinely new entry to humanity's still growing map of the galaxy, found not by chance but by an international team who trusted the math, built the models, and pointed the most powerful telescope ever constructed at precisely the right patch of sky, at precisely the right moment to finally see it for themselves. If this discovery genuinely surprised you, hit subscribe, because the next planet Webb finds on its own may be closer, smaller, and even harder to believe.